In this video, we continue our discussion of volume by looking at volumes of revolution by disks and washers. In manufacturing, when you're creating shapes to put into a machine, you often have to create a part that is symmetrical around some central axis. You do this by putting it on a machine called a lathe, and then you carve out a shape that is symmetric all the way around some central axis. These produce solids where you're rotating around some center line. For example, let's look at this graph that you see right here in the picture. If you were to take this and you were to rotate it on that machine called a lathe around a line down here represented by the x-axis, you would produce the solid that you see here in the right two images. Can you see the curve here that forms the upper edge of the solid of revolution? And do you see its mirror image across the x-axis in the second image here? Let's highlight the image so you can see it a little bit better. In this image, I've now highlighted the curve that produced the volume of revolution by accenting and outlining the shape of it in the upper part of the volume of solid. If you look at the lower solid, you can see the mirror image of this shape as it was reflected about the x-axis. Here's the image of the shape as it's been reflected. All I did was simply took this picture and flipped it over the axis. Now, this axis of rotation is the line about which we are rotating the entire curve to produce this solid of revolution. Let's take a look at what some of these would look like in the real world. We'll have experience in rotating these about the x-axis and the y-axis, or about a line parallel to either of those. That is, some line x equals c or y equals c. We will not rotate any of ours about a line that is not parallel to the x-axis or y-axis. Let's move to the webcam and I'll show you some real solids produced by rotating a curve around an axis. Let's take a look at what would happen if we took a curve in the xy plane and we revolved it around an axis, either the x-axis or the y-axis, or a line that's parallel to one of those axes. I'm going to start with a pretty basic shape. This one, I don't even know what it was based on. I think originally this is if I'm not mistaken, this is a wedding bell. So if you are trying to visualize what a volume of revolution is, imagine taking a shape like this and let this be the x-axis. And let's rotate it around the x-axis. So we're going to grab hold of one edge and we're going to rotate. So as I rotate, notice that it is turning into a volume. And as I continue to rotate, it eventually comes all the way back around to the beginning. And I end up with a solid shape. Now, what is this solid? Well, like I said, I think this is originally a wedding bell decoration. But they make excellent volumes of revolution by revolving around some axis. So this is what we have. Now, let's go back to the original shape so you can kind of see how the original shape gives rise to this three-dimensional solid so that we can talk about how to find the volume of it. We're going to go back to the original shape, which again, assume this is the x-axis, and this is your curve that is out there. And you're going to be starting here at some x value. Maybe this is x equals 0, and you're going to go to some other x value, maybe x equal to b. This could also have been x equal a, and this is x equal b. And you're taking the curve between x equal a and x equal b, and you're rotating the curve around the axis. It's almost like you've grabbed the axis and you're turning it, you're rotating it like a skewer on a spit, a barbecue spit. And when you're done, you should have this three-dimensional solid. And our job is going to be to find the volume of this solid. Let's practice for just a moment finding what kinds of solids we get from revolving different shapes. Now, I'll warn you, some of you are going to be very good at this, and you can instantly see in your mind what the solid will look like. Others of you are really going to struggle with this. This sort of visualization is one of the last skills to develop as the brain continues to develop throughout adolescence. Now, when I say adolescence, I don't mean until you're 18 or 19. Physically, the brain develops until about age 25. So as far as your brain is concerned, you're an adolescent until you're about 25. Now, that's an average. That means some of you will be done with your brain major development by age 23, and some of you it'll be 27. That's okay, it's an average. What that does mean, though, is that some of you will be able to do this now, and some of you will not. And I can totally relate, because I could not do it at age 19 or 20 or 21. But when I got to be 27, suddenly I could just see it. And I couldn't understand for a long time why I couldn't see it before. And the reason is neuroscience. The brain had to develop that visualization skill, and it doesn't occur until the brain reaches its second period of most rapid growth. First period, of course, is from birth to age 5, and the second most rapid period of growth and development for the brain is in adolescence. That's why you sleep all the time. So again, on average, adolescence is about from age 13 to 15 up until about age 25. So let's take a look at another shape. Let's imagine that we have this shape here. The bottom edge is going to be the x-axis, and let's rotate it. Now we're rotating around. Can you see what's going to develop, what it's going to look like when we get it completely rotated? Here it is, and I'm going to turn it in different directions so that you can see sort of what it looks like from all different angles. Again, this is the original orientation right here, where our shape that we originally revolved was this shape right here. Okay? Let's try yet another one. I've got lots of shapes to play with. So here's a shape. This is a relatively simple one. Can you imagine what this is going to look like? It's going to look sort of like a circle, but it's going to be cut off at the ends. So the top and the bottom should be flat. So when we rotate it, we end up with a shape, and this one's having a hard time rotating, that looks something like this. Do you see the flat bottom and the flat top? So again, they're flat because it was cut off there. It does look somewhat circular because the edges of it, when I had it in the closed shape, this part of it, the curve, looked sort of semicircular. Let's look at another one. This one I like to rotate because this one is the best example of what it's going to look like when we start computing the volume of these things. What we're going to do is we're going to take our original shapes, which looked like this, and we're going to slice them. We're going to cut them into small pieces, and we're going to rotate each individual piece. As we rotate each individual piece, it is approximated by a cylinder, a right circular cylinder. Let's rotate this so you can see what the right circular cylinder looks like. As I rotate this around the axis, notice that it has the shape before we start of basically a strip, almost a rectangle, except it's got a curved top. If it were truly a rectangle like this one, it would form the shape that we're going to use to approximate these volumes of revolution, and that would be the right circular cylinder. This one, when it's rotated, you'll see that it does take on that nearly right circular cylinder shape. And I'll show you what the actual rectangle rotated looks like as well. Now you can see from the edge that this is a circle. The only reason it's not a right circular cylinder is because of the curved top. Let's rotate one that does have a straight top. That would be this one right here. This one has a straight top and it's more or less a rectangle. As I rotate this one around, you're going to get a right circular cylinder. This is the shape we're going to use to approximate the volumes of our volumes of revolution when we compute them by disks and washers. As I rotate around, do you see that this becomes a right circular cylinder? I have a circle base here and another circle base here, same size, same shape, and they're parallel. The distance between them, of course, is here. This gives me a right circular cylinder. This is going to be similar in shape to this right here. This is a right circular cylinder, and it's turned this way. Notice that the distance between the two bases is going to be the thickness of the cylinder. That's the height of the cylinder. When we're looking at it straight on edge before it's been rotated, that height of the cylinder is this measure here. If this forms the x-axis, then this becomes the change in the x value, or dx, which is, of course, the differential. Let's practice looking at a few more shapes so that you can start to develop the skill of seeing in your mind's eye what it looks like when you rotate some kind of curve about an axis. For fun, let's rotate this one instead of about the x-axis. Let's rotate around a vertical axis. That means we'll be rotating this way. The process will be the same. We'll still take the shape, and we will still eventually be wanting to, if I can get it open, approximate it using a bunch of cylinders. This one appears to be stuck together. I'm not sure if I can get it apart. I'm pulling. It's glued together. Okay, if this one's not going to work, we'll toss it aside and pick up another one. I've got plenty. All right, looking at this guy, let's let this be our axis of rotation, and let's spin it. Here's the shape. Here's the axis of rotation. If we decide to approximate, we will make slices that are perpendicular to the axis of rotation. Not parallel, but perpendicular. So we'd be slicing horizontally, whereas when the x-axis is the axis of rotation, we slice vertically. Let's start rotating around our axis. Can you see the shape starting to develop and come out? Here's what our shape looks like when we get it fully revolved. I don't know what you'd call it. It's got sort of a mushroom shape, if you will. This part right here is a hemisphere, half of a sphere or half of a ball. But this part up here is sort of, well, I don't know, curved. Let's unopen it and get back to the original shape. Why did we end up with a hemisphere? The bottom edge right here was a quarter of a circle. And when I took that quarter of a circle and I rotated it around, it gave me that hemispherical shape on the bottom. The top, however, was sort of a curve that looked like, in this shape, it was coming out like this, which means as I rotate it, I get that sort of edge that's coming and slanting in, sort of like a volcano shape. Let's take a look at another example. This one is a trapezoidal shape. Why is it a trapezoid? We have two pairs of parallel sides, the side where my hand is, which is imitating the y-axis, and this side here. These two sides are not parallel. Can you visualize what it's going to look like when I rotate it about this vertical axis? Again, as I rotate, remember that it takes it and rotates around the axis of rotation. This is going to end up looking sort of like this. So you can see that they are circular when you rotate. They're always circular when you rotate because you're rotating in a circular motion. And we'll be using the cylinder like this to approximate the volume. We'll make lots and lots of cuts in it to approximate. Let's look at one more example and see, let's do two more just for fun. What is this going to look like when you rotate it? This time we're going to switch again to the horizontal axis of rotation like the x-axis. Can you see what this looks like? This is an actual decoration, and it does have a shape. So close your eyes, try to revolve, and see what you think it might look like. All right, let's do it. We're rotating, rotating, rotating. You got it. It's a baby bottle. All right? Some of you got it, and some of you are like, no way. Yeah, way. It's a baby bottle. Now, let's take another example, and then we'll talk about how we slice them up. Here's one more example for you to practice seeing these in your mind's eye. We've got this sort of wavy behavior up here, then it comes down, and then it waves in a more regular pattern, but then it gets cut off towards the bottom. This is going to give us a more or less flat edge on the bottom, but the rest of it is going to be curved. Let's see what happens. We're going to rotate this one around a vertical axis because I already know what it looks like. Let's rotate and see what we get. Can you see it in your mind's eye? As I rotate, and yes, the color does help. Yeah, believe it or not, this guy is a pineapple. So this is a decoration. You can see the flat ends created by that flat edge, and the top become the leaves. Now, how do we approximate these? By using these discs right here. Remember, there's circles on this side, circles on that side, and they're parallel. Same size, same shape, parallel, so it's a cylinder. Remember that the volume of the cylinder is area of the base times the height, where the height is the distance between the two bases, same size, same shape, and parallel. That makes the volume of this disc pi r squared times this distance. This distance will be our differential. So we'll have pi r squared dx or pi r squared dy, one or the other. Let's take a look at what the original shape we revolved would look like if I sliced it and just rotated one slice. This was the original, and remember when we rotated it, this gave us a wedding bell. All right, this was the wedding bell picture. Let's go back to the original shape, and let's imagine slicing it perpendicular at a right angle to the axis of rotation, which is horizontal. So we'll slice it vertically into small slices. Now, because it's difficult to do this, my slice had to be pretty darn big. But what we're looking at here is slicing it here. I'm going to take one of these slices and I'm going to rotate it. As I rotate the single slice, I end up on the edge. You can see it's a circle. In fact, it is a right circular cylinder, just about. How would it not be a right circular cylinder? The top edge is ever so slightly not parallel to the base. In a true right circular cylinder, the top is parallel to the bottom. It's a rectangle. Mine's almost a rectangle, but not quite. Now, none of these are truly going to be rectangles, but as I make the slices narrower and narrower, they become more and more rectangular. And that, of course, sounds like a Riemann sum. And that's what we're going to be doing. We begin our study of volumes of revolution by looking at volumes of revolution by what are called disks. That means that we're using cylinders with circular cross-sections to approximate the volumes. Our volumes of revolution will be rotated about either the x-axis, the y-axis, or a line that's parallel to one of the two. To determine the different pieces of information we need to find the volume, we'll draw a thin rectangle called a strip onto the graph. This will represent one slice of the curve we want to rotate. We'll also learn about something called the washer method. The washer method is for when we have both an inner and an outer radius. The washer method is based on the disk method, and in both cases, the strip is drawn perpendicular to the axis of rotation because we are slicing perpendicular to the axis of rotation. In the next section, we'll be studying the shell method, and in that case, the strip is drawn parallel to the axis of rotation. To keep the two methods straight, I teach my students to remember that both shell and the word parallel have a double L, and the symbol for parallel is a double L. That means that in the disk washer method, we are going to draw the strip perpendicular to the axis of rotation, and in the shell method, we'll draw it parallel. Now, in theory, volumes of revolution can be computed using either the disk washer method or the shell method. In practice, however, one method may be far simpler than the other. In this situation, you'll have to look at the picture and try to imagine by drawing strips which one would be the easier to compute. Let's take a look now about a revolution about the x-axis. This Geogebra 3D applet will help you visualize what you're doing. In this particular curve, we have the equation 0.1 times x minus 1 times x minus 5 times x minus 9 plus 2. It has this graph here. What we wish to do is we want to take that graph from x equals 0 to x equals 9 and revolve it around the x-axis. This is what it will look like when we get it revolved. Let's go to the Geogebra applet and let's enter this equation. When you open up that applet, you'll see that it's in Geogebra in the upper left-hand corner. This is the normal screen on which it opens. We need to change our upper curve to being the 0.1 times x minus 1 times x minus 5 times x minus 9 plus 2. We'll enter that upper curve here in the box. Highlight the square root of 2, take it out, and replace it with the actual curve. When you hit enter after putting it in, you will be able to see the curve appearing here in the left graph. Automatically, it's set up for a equals 0 and b equals 9. That's because it is going based on what makes sense. However, you can change these by highlighting the number in the box and changing it and hitting enter, or by moving the slider bars. We do want to go from 0 to 9, so we're going to leave it alone. Over here in the right picture, you can see our volume of revolution. If you turn it so that the axis is pointing directly at you, you can see the curve that produced our picture as well as its mirror image on the bottom. This is what is producing our volume of revolution. Yes, I know, it also gives you the solution down here at the bottom, which means you have no excuse for having your homework incorrect. However, if you rotate it, you can see what it looks like from all different angles, which should help you to learn and develop that skill of being able to see the volume of revolution based on what it looks like for the curve in the XY plane. Let's now go back to the screen and take a look at computing the volume. To compute the volume using disks, we need to draw some sample strips or rectangles, those thin rectangles, perpendicular to the axis of rotation. Our axis of rotation is the x-axis. There's a second image and a second applet here in Geogebra that will help you to visualize what each individual strip looks like. Click on this applet now and let's take a look at that one and see how it helps. When the applet opens, again you can recognize that it's in Geogebra in the upper left corner. In this particular one, notice that it says the width of each rectangle will be given by b minus a divided by n. That sounds a lot like a Riemann sum, because it is a Riemann sum. You'll see here that we have function for f of x, a value for a value for b, and an n for how many rectangles we want. 5 or 6 is a good number to start with, But we do need to change our a to be x equals 0 and our b to be x equals 9 and our function to represent the function that we have. Pause the video here and enter those values. Now that you've changed the function and the values for a and b, let's change the number of rectangles and make it slightly larger at n equals 6. Now click on the slider bar for spin rectangles and let's rotate it. Do you see what's happening? Do you see that we are developing those right circular cylinders as we rotate around the x-axis? At any point, if you wish to stop and grab hold of the picture and rotate it, you are allowed to do that at any time. Notice that we do not have the complete cylinders because we haven't finished the spin. If I finish the spin all the way around, do you see that each rectangle created its own right circular cylinder? The volume of each right circular cylinder will be the area of the circle, pi r squared, multiplied by the height of the cylinder, which is the distance between the two circles, which is our differential dx. These two slider bars here on the bottom allow you to fill in more of the disc or the rectangles. Disc filling makes them more solid so you can't see through them. If you make them less filled, you can see through them to see all of the discs. If we unspin the rectangular regions, we can also fill the rectangles. Filling the rectangles means you can't see through them. If you make them partially filled, you can see through them to the shape as you revolve it. Let's go back to our other screen and let's find out how to compute the volume by revolving. Notice that when we drew our sample rectangles or strips, that the narrow end was parallel to the x-axis, and that makes the differential dx. The differential is always the short end of the strip, even when we're computing volumes by slicing, as we saw in the previous video. There is one more online calculator for graphing that will help you to look and see what these look like. This next one is one that we'll use extensively in Calculus 3, so you may want to get some practice at it now. The next one is called Calc Plot 3D. Since we use it so often in Calculus 3, you may want to practice with it quite often. Let's go out to Calc Plot 3D and make sure that we can see what it looks like out there. When you get to Calc Plot 3D, you will always see this image here. This is the home base image for the program Calc Plot 3D. It is a free online calculator for all kinds of things. We will use it on almost every exam, if not every exam, in Calculus 3. The one you want, since there used to be two versions of it on the internet, is the one that has down at the bottom something that says surface of revolution. Let me pull it up so that you can find it. It's all the way at the bottom, surface of revolution. You'll click on the drop-down menu that says select, and you'll select a surface of revolution. When you click on it, it will automatically open up a 2D graph right here, and it will also open up a series of boxes down here. It will not, however, take off our previous picture, which, yes, you can grab that sucker and rotate and spin it however you'd like. I hope I'm not making you dizzy. To get rid of that picture, you want to put the cursor over the left side of the screen and scroll. When you come down here, you can see that there is a blue check mark next to this equation. That means that this is the one producing the graph in the picture to the right. If you click on the X, it just deletes it. Bing, and now it's gone. Notice there's nothing showing up because this box is empty. It is not being graphed yet. For those of you who don't have the notes for this video, here is the URL so that you can find Calc Plot 3D. Now let's take a look at using Calc Plot 3D to produce one of those surfaces of revolution. We need to enter our top and our bottom here. Calc Plot 3D allows you to have any graph you want on top and any graph you want on bottom. It allows you to choose, in this case, that you're going with the 2D and x varying from this value to this value. What we want on top is that 0.1 times x minus 1 times x minus 5 times x minus 9, all plus 2. Then our bottom will be the x-axis, which is the equation y equals 0. Our x value will vary from x equals 0 to x equals 9. Our axis of revolution is given here, and I'm going to show you how it will change drastically if I change the axis of revolution. Pause the video now and enter the information for the first 4 boxes. Your boxes should now look like these first 4 up here. The default is y equals 0. This is the x-axis, which is the one we want. Notice that I still do not have a blue check mark here in the box. Put your cursor in any of the boxes and click Enter. This will graph it. You can also click on the button that says Graph. Now, this looks a little crazy. Why does it look so crazy and what's going on? We've got a number of layers and we've got slices 15 to 40. Let's put the whole screen on so that we can see what it looks like. To have it show up, you can scroll in on your mouse wheel by simply scrolling. The problem is that our box here is too small. I need my box to extend out to at least x equals 9, and I need it to go up higher on the y, and I have no idea what I need on the z. There are several ways that we can accomplish this. One way is to go up here and click on the first box that you see here next to the words 3D mode. When you click on this, it will drop down a menu for you to enter the actual x values you want. Since I know I'm going from 0 to 9, I probably want to extend a little bit past that. So I'm going to make mine go from -2 up to 12. I don't really know what y value I need, but I'm going to make a guess that I need something that's at least 10 tall, but that could be completely wrong. If I have that for the height, then I probably need at least that for the bottom. I don't know what I need for z, but since this is a volume of revolution, it makes sense that whatever the maximum height is for y, that's going to be the maximum for the z as well. So I'm going to change my minimum for x and z, rather for y and z, to go from -10 to 10. Now I have no idea what it's going to look like, so I'm just going to click Enter and see what happens. Aha! Now you can see what it looks like inside the box. Clearly I don't need that much. I went in or went out too far. Also notice that I've got all these numbers showing up, which is a little cluttered and pretty confusing. If you come in here, you can change the tick marks to maybe go by 2s or by 5s. However, note that it is going to start at whatever your minimum value is. If I tell it to go by 5s, it's going to mark -2 and then 3 and then 8, which is not what I want. I'm going to change my x minimum to be -5, and then I'm going to tell my tick marks to go every 5 so that it marks them off appropriately. I'm going to do the same thing for the y, but since -10 is a multiple of 5, that seems like it would be okay. And I'll do the same thing for the z. Now hit Enter again, and you'll see that it's taken a lot of those off. Remember that you can scroll in and out with the mouse screen, but it will not change the limits on your x, y, and z. That needs to be done with this drop-down menu. You can also change it by clicking on the hourglass or magnifying glass here at the top. When you click on the one with the plus, it makes the picture bigger. This will change your limits of integration that you can see here. If you click with the minus magnifying glass, it makes it smaller and can make it super small. Clicking on the magnifying glass does change the limits of integration. It looks to me like this is a pretty good picture of what we've got going on. Now notice, however, that my x value is not going up high enough in my box. I may want to change that by clicking on the graph menu and changing my x max to being something like, oh, let's say 15. And not 16, 15. Rats, I keep hitting the wrong number. And then I'll hit enter. It is not necessary to have the box be symmetric. Let's close this up by clicking on it, and now we can come down here. What does the slider bar do? The slider bar simply moves the ball around so I can compute at different points. What I want to do is I want to imagine rotating the region. Let's click on Show Representative Rectangle. You can pick where between 0 and 9 you want the rectangle to show up. It will go between the two limits that you set here. Mine's right in the middle, which is the default. Now it says revolve the representative rectangle. Do you see it revolving around? If I get all the way around, I'll have that right circular cylinder. Let's scroll in using the mouse wheel so that we can see it a little bit better. You can see here by rotating that it is in fact a right circular cylinder, and it's super thin. Now what would happen if I put more of those on there? If you scroll down a little more, there's a box that says Show in Washers/Shells. The washers is the same as discs. Shells are not the same. What we want to do is show different ones. The default here is 4. Let's see what it would look like with 6. If I increase it to 6, then I can revolve those as well. Let's see what it looks like if I unrevolve these. Now that I've unrevolved the representative rectangle, let's revolve all of the washers or discs. Do you see how they're revolving all the way around? Yes, I know it kind of went backwards, but you can't control everything. So in this sense, we now have our shape right here. I know, it looks really bizarre. Okay, and it doesn't look like the picture that we got off of Geogebra. Let's go back to Geogebra again and see what it looks like. It's supposed to look like that. That is not what it looks like in Calc Plot 3D because we only have 6 rectangles being revolved. Let's increase the number of rectangles. Aha! Are you starting to see the shape coming out? It does in fact look like the one off of Geogebra 3D. If we increase the number of discs until we get very large, which I think, I'm not sure how many is the maximum. Here it's going up to 50. It does look like that. And you'll notice that it is giving you an approximation for the volume down here at the bottom based on that number of shells. You'll see the volume of the region down at the bottom. You can also see what the function value is at any given point up here. So if you want to know what the function value is at a particular point, you can change it by selecting your point, and then it will compute wherever it is. So if you want to know what's the function value when x is 1.35, then you can see it up here in the upper left corner and in the green banner at the top. This is giving us the volume of revolution. Now, you can also change things by clicking on the gear symbol here. This slider bar at the top makes the picture transparent, which allows you to see partway through it. It allows you to see partway through the picture to what's on the back side. There are other options as well, which is reverse the colors. That's one option, which will change the appearance by reversing the colors. or putting on a wireframe only. A wireframe only will make the picture look like wires, or you can make it into a constant color. You can also hide the edges by hiding the edges of the picture. Let's see what it looks like if we make it a constant color and we click on Hide My Edges. You can choose the color. I'm going to choose purple, and let's close it up. Let's see if that actually accomplishes what we wanted. It did not. And why not? Because I'm still showing the revolved washers with the shells. It is possible to get it to show. You'll simply have to play around with the boxes and figure out how to do it. We'll take off the representative rectangle, and we'll show the washers, and there it is. There's my purple volume of revolution, which I have made semi-transparent so I can see the shape. Can you see the shape that created this volume of revolution hiding inside of it? Let's go back now to our regular screen and let's compute the volume using just the curve. In this particular picture, what we're doing is revolving these rectangles that we drew around our axis of rotation, which is the x-axis. Because the narrow end of all these thin rectangles or strips is dx, the differential is dx. What is the radius, however, of each of the cylinders? If you look at the picture here, you can see that the radius of the cylinder is the height of that curve. That means the height of the curve, or the function value at that point, is the radius. That becomes the radius of the circular cylinder, and that's how we'll compute the volume. Remember, the volume of the cylinder is the area of the base, pi r squared, times the height of the cylinder, which is the differential dx. This is what it looks like with all the strips revolved and a larger number than 6. The smaller the slices get, the closer to the true volume we get, until it looks like this. Let's put on the screen now the disk method for revolving around the x-axis. Let the function f of x be continuous and not negative. Define R as the region bounded above by the graph of f of x, below by the x-axis, on the left side by the line x equal a, which could be the y-axis, and on the right side by the line x equal b. In our example, the left side was x equals 0, and the right side was x equal 9. The graph f of x was 0.1 times x minus 1 times x minus 5 times x minus 9 plus 2. Ours was bounded below by the x-axis y equals 0. The volume of the solid of revolution formed by revolving this region R around the x-axis is given by the definite integral from a to b of the area of the circular cylinders, pi r squared, times the height, the differential, the distance between the two circular bases. Our formula, because the radius is given by the function, is pi f of x quantity squared dx. In other words, this is really pi r squared dx. Let's take a look at example number 3. In this example, we want to find the volume of revolution for the solid produced by revolving the region R bounded by the function f of x equal x plus 1 quantity squared between the vertical lines x equals 0 and x equal 2 and the x-axis by revolving about the x-axis. I'm going to sketch it by hand first, and then I'll show you what it looks like in Calc Plot 3D. To sketch by hand, this is basically a parabola that's been shifted left 1. Draw your x and y axis here and shift your parabola left 1. Make sure that you use exact points so that your graph is at least as accurate as your hand drawing, which in my case is not terribly accurate. We want to bound our region by this parabola, by the line x equals 0, the line x equal 2, and the x-axis. The line x equals 0 is just the y-axis, which is here. The line x equal 2 is the vertical line here, which will extend on the graph up to the point 2, 9. This point right here is important. We'll need to know that that is 2, 9. Can you see what's going to happen when you revolve it? If you revolve the picture, it kind of looks like this. Now what I did to get this picture is I exaggerated the distance on the x-axis so that the distances on the x and y-axis were not remotely the same. This made it longer, but it did make it easier to draw. And then I simply took the mirror image of this across it. In other words, you'll want to draw the picture of this, and then you'll draw its mirror image down below. And then you'll connect one mirror image with the other. This will give you your solid of revolution, which does look something like this or like this. Let's look at in Calc Plot 3D, where we're keeping the axes more or less the same. Here's what it looks like in Desmos when I graph the region. I'm graphing between here and here. This is the graph, and this is the reflection of it. Notice I'm going between x equals 0 and x equal 2. This is just a piece of the parabola x plus 1 quantity squared. When I get it graphed, it looks something like this or like this. Here you can see the actual shape that's being used to revolve about the x-axis. The formula is pretty simple. Go from x equals 0 to x equal 2, pi times r, which is given by the function value on the parabola, x plus 1 quantity squared, squared. Make sure that you remember that just because the function has a square, that doesn't count for the pi r squared that's in the formula. You have to square it again. Take a moment to pause the video and work out the calculus to be sure that you also come up with the value 242 pi divided by 5. We have a similar rule for revolving about the y-axis, but in this case we have to take the function and we have to isolate x so that it can be written in terms of y. This means that you will take your equation, replace the f of x with y equals, and then solve the equation for x. Then what's on the other side becomes your function value. In terms of the rule, we will allow g of y to be continuous and not negative. We define Q as the region bounded on the right side by the graph of g of y, on the left side by the y-axis or a different function, h of y, below by the line y equals c, and above by the line y equal d. If we're revolving about the y-axis, then typically our left side will be the y-axis. Then the volume of the solid of revolution, formed by revolving that region Q around the y-axis, is given by the definite integral from y equals c to y equal d of the area function, which is pi r squared again, times the differential dy. Let's look at an example of a problem where we are revolving about the y-axis. We want to revolve the region bounded by the curves f of x equal e to the x, y equal 3, and the y-axis about the y-axis. First, we graph the function e to the x, which of course as an exponential follows this basic pattern. Y equal 3 is a horizontal line, and the y-axis, of course, is the vertical line. That gives us a bounded region here, which has been shaded yellow. Notice that our rectangle is going to run horizontal this time because our axis of rotation, the y-axis, is vertical. Always draw the strip for the disc or washer method perpendicular to the axis of rotation. Notice that the narrow end of the strip, the short end, is vertical, which means that our differential must be dy. I took a picture of this and then I reflected it across the axis But since my axis wasn't too straight, it didn't come out too well. But you'll see this in the image on the right. Notice that this is crossing the y-axis at the point 0, 1. And it has a flat top right here. This is basically what the shape is going to look like. When you're trying to revolve the shape, take the image and draw its mirror image on the other side. This will give you a better idea of what it looks like. Now let's take and think about how to set up the integral to compute it. Because we're revolving about the y-axis, our differential is dy, and that means all the variables inside the equation have to be y variables. That means we have to take our function and solve for x in terms of y. Our function, however, is f of x equal e to the x. Replace the f of x with the variable y, and then convert the form from exponential form to logarithmic form. This solves it for x in terms of the variable y. So the function f of x equal e to the x becomes the function of y, g of y equal to the natural log of y. What will our limits of integration be? We need to go from our lowest y value on the bottommost strip. So the bottommost strip, oops, my bad, I moved my picture, which I did not intend to do. The bottommost strip, and it keeps wanting to do that. Sorry about that. I'm not sure why it won't let me just draw. If I want to draw it, it should make a rectangle wherever I've got a picture. Now, on the bottommost strip would be at the value y equal to 1, and the topmost strip would occur up here at y equal 3. That means my limits of integration should go from y equal 1 to y equal 3, from the lowest y value, lowest strip in the region shaded yellow, to the highest y value, highest strip or rectangle in the shaded region yellow. This then gives me pi r squared. The r, the radius this time, is running horizontally. Notice that it's going to be rotating this direction here around the y-axis. I use a curved arrow to indicate the axis of rotation, so I don't forget and accidentally draw the strips or rectangles going the wrong direction. Our function is natural log of y, and we square it. Pause the video here and compute the definite integral. Okay, I know you probably did not pause the video for long because you probably looked at that and went, I don't know what to do. I can't remember. It's been too long. This is an integration by parts. Why? Because we have a function natural log of y. Remember that when you integrate natural log of y, you have to apply integration by parts. Pi is just a constant which can be brought outside the integral from the beginning. We'll allow the natural log of y quantity squared, which can be written this way or this way, to be u. That makes dv just the differential dy. When we integrate the dv, we get y. When we take the derivative of u, though, we have to apply the chain rule. We have 3 layers deep. The derivative on the outside is the derivative of the second power, which is 2 reduced the power by 1. On the inside of that, we have the natural log of y. The derivative of natural log of y is 1 over y. And on the inside of that, we have a y, and the derivative of that is dy. This gives us the derivative of u as 2 natural log of y times the quantity 1 over y times the differential dy. Remember that integration by parts is u times v minus the integral of v times du. When you set that up, you end up with this value right here. This needs to be evaluated between y equal 1 and y equal 3, and this needs to be integrated between y equal 1 and y equal 3, since that's what the original integral had. When you compute these, you get the next step. Scrolling down, you can see that our volume then is going to give us another application of integration by parts because we end up with the natural log of y. Natural log of y becomes u, the derivative is 1 over y dy. The differential dv is the dy variable. The differential integrated gives us v equal to y. Then we apply integration by parts again, and we come up with the final answer you see here, highlighted in yellow. Make sure that you keep the limits of integration the same at each step. Here's what it looks like when I put this into Calc Plot 3D and I revolve it. Notice that it gives me basically sort of like a vase shape, but the vase is solid because the rectangles, the thin strips, touch the axis of revolution. Let's take a look at what it looks like in Calc Plot 3D. We're going to come over to the graph and we will graph it. Calc Plot 3D does not yet have the ability to put in the functions as functions of y. You'll have to convert them into functions of x instead. But this isn't too difficult. Let's look back at our regions again so we can know what they look like. We have the horizontal line y equals 3 on top and the curve e to the x on the bottom. We're going to go from x equals 0 to whatever that point is there. We know that's when e to the x equals 3. In order to figure out what that gives us, we need to solve the equation e to the x equals 3 for x. To do that, convert this into natural log form, which is the natural log of 3 is x. That means we'll go to this point right here, which is going to be at the natural log of 3, 3. So we need to go from x equals 0 to the natural log of 3. Now, Calc Plot 3D is a big believer in using parentheses around the arguments, which will probably make some of you happy, since I'm kind of lax about that in class. But it's going to expect to see parentheses around the 3. So our x value is from 0 to the natural log of 3, and our y value on the bottom is e to the x, and on the top is 3. Now that we can see it over here on the side, we can also see that it's way too small. You can put your mouse on the picture and scroll in, or you can scroll up and click on the magnifying glass with the plus sign. Keep in mind, though, that the magnifying glass with the plus sign may end up giving you a picture that goes off the screen if it doesn't reset your box appropriately. Let's look at the box and let's reset the box. I'm going to make x minimum go between 0 on the bottom and let's try maybe 3 for the top. So 0 for x and 3 for the x value. Actually, let's look at our picture. That's way too much. Let's just go to 2. That's probably still too much, but 1 is not enough. That puts it there. What about the y value? Well, it's clearly above the axis, so I'm going to let y start at 0, and I'm going to go up to 4 and see if that puts it back in the picture. It does, but notice that it's all the way at the top. What's the problem? The problem is that the focal point for Calc Plot 3D is always at the origin unless you tell it to move it. That's what focus point means down here at the bottom of the drop-down menu for the axes. When we're looking at this one, it looks like we would rather have it focused maybe at y equal 2. So I can tell it to focus on the point 0, 0, 2. That should bring it back down into the center. Oops, no it didn't. Why not? Because I told it to focus on the wrong axis. I want it to focus on y equal 2. So let's change the z coordinate back to 0 and change the y coordinate to 2 and see if we can get our focal point to be in the middle. That's much better. Now I can see it in the center of my picture. That's close enough to see what it looks like. Now you can see over here on the edge, if you turn it side on, what the shape is. We've got the exponential here and the horizontal line y equal 3 there. Let's scroll down and take off that solid color by clicking on the gear symbol and telling it to have a normal appearance. Now it looks like that, and let's tell it not to hide the edges. If we put the edges on, we can see everything. Reversing colors means that it will change it to a different color. Wireframe means that you see only the frame of the wires, but you can also see as a solid color the graph that produced the volume of revolution. You may prefer one of these different versions. I'm kind of liking the reversed colors. Remember that the slider bar makes it more or less transparent so that you can see through to the other side. I would like some transparency so we can see through it. There's my shape that's revolving. Let's take a look now at what it would look like if I revolved around a different axis to show you that it would be completely different. Because Calc Plot 3D does not have the ability to write the equation as a function of y, you should not use the representative rectangles because it will give you a graph that is actually produced using the method called shelves. We'll see that in the next video. We can, however, rotate the region by unrotating and going back to the original shape that produced our curve. We can do this by revolving it about the y-axis, and we can stop at any point and we can look and see what it looks like as we revolve. Now let's see how revolving around an axis other than the y-axis produces a totally different solid. I'm going to come up here to the axis of revolution, and instead of revolving about x equals 0, I'm now going to revolve around y equals 0. If I change that, nothing changes in the graph until I enter it. Click on any of the boxes and then hit the enter. Whoa! Okay, yeah, that's different. It's a completely different graph. Is it really the one that I thought I originally had? Let's make it smaller so we can see the whole thing at once. And let's unrotate it so that we can see what it looks like. Hopefully I can get it to stay still. Let's unrevolve it. Remember that this was revolving around the x-axis, and notice that it actually is hollow, and that's because the strips do not touch the x-axis, which is the axis of revolution. When the strips don't touch the axis of revolution, you get a hollow space or a hole. What if I were to rotate around a different line, not the x-axis or the y-axis? Maybe I want to rotate around the line y equal 5. What would that look like? Something, again, completely different. This looks like this now, which is different from both of the first two. Each time you revolve around a different line, you will typically get a completely different shape. If I were to revolve around a different line that's parallel to the y-axis, I might get something that's a little bit more similar. Let's rotate around the line x equal to 1. This is going to be a very strange graph. When I rotate, you can see that I've got the shape, the same basic shape, and I'm rotating around this axis. Let's unrevolve it so you can see the shape beginning and rotating. Now as it rotates, it's rotating around the axis x equal 1. I'm going to turn it on edge so you can see both the circulars, cylinders being developed, and so you can see the shape that's producing the curve. Do you see what a difference it makes? What if I were to revolve this around the line x equal -1? Would that produce something different? Yes, completely different again. Now I can take the same shape and notice that it's hollow again because the shape that's producing the picture does not touch the axis of rotation. We'll unrevolve it, and then we can see, here's the axis of rotation, x equal -1. Here's my picture, my shape that is being revolved, which is the shape trapped between the y-axis, y equal e to the x, and y equal 3. Now I'm going to turn it a little bit sideways so you can see both shapes and revolve it again. As I revolve around, you can see the cylinders coming around, and you can see that they're developing their shape. But it is hollow because they don't touch the axis of revolution. When we use the disk method, but our axis of rotation is not touched by the region that's being revolved, we are actually using what's called washers, and that's what gives us this empty region here. Let's go back to our main screen and talk about what that looks like. When we're doing this particular section, we could call it revolutions where the strip does not always touch the axis of revolution, since that's essentially what they are. We're going to take the regions from examples 3 and 4, and we're going to rotate around the other axis. If we do that, not every strip touches the axis of revolution. The example from example 3 touches the y-axis on the lower part of the picture down here, but it does not touch the y-axis up here. Originally, we rotated around the x-axis, but now we're rotating around the y. What about the one from example 4? Originally, we rotated about the y-axis, but now we want to rotate about the x-axis. Notice that none of the strips ever touch this axis of rotation. This will give us a hollow space on the inside. This will have a hollow space only in the region where it does not touch the axis of rotation. Notice that our strips have a partial distance that does not touch that axis of rotation. On the bottom, where it does touch the axis of rotation, the strip touches the axis of rotation. Let's take a look now at how to find the volume of such a region. Basically, you end up with two solids, an inner solid formed by the curve closest to the axis of rotation, and an outer solid formed by the curve farthest from the axis of rotation. We can call these inner radius and outer radius. The inner radius and outer radius are given by the ends of the strip closest to the axis of rotation and the end of the strip farthest from the axis of rotation. Let's take a look at what those would look like in our next picture. Right here, what we can see is that the inner radius is from the axis of rotation to the closest end of the rectangle, always from the axis of rotation to the closest end. If it touches the axis of rotation, that distance is 0, which is why we didn't take it into account in the disk method. If the radius is 0, then the volume of that circular cylinder will also be 0. What about the outer radius? The outer radius again comes from the axis of revolution to the farthest end of the strip. That would be from here to here, or from here to here. For the disk method, that is what we called the outer radius, or the radius. So basically, the disk method is the washer method, where the inner radius is simply 0. In the example 4 picture, notice that the inner radius goes from the new axis of rotation to the closest end of that rectangular strip. The outer radius goes from the axis rotation to the farthest end of the strip. In effect, the outer radius is carving out the outer surface of our solid, and the inner radius is carving out the inside, or that hollow part. We can either compute both volumes and then subtract the inner volume from the outer volume, or we can do both jobs at the same time. If we do both jobs at the same time, we're actually using a shape called a washer instead of a disk, by which I mean one of these shapes that you see in the picture here. Now, a real washer is much smaller than this, at least the kind that go inside your faucet to keep it from leaking. It is still a circular cylinder, but with a hole punched in the middle of it. You can see the hole here. The inner radius goes from the center to the closest inside edge, and the outer radius again from the center to the outside edge. Let's take a look on the webcam view of what a circular cylinder washer actually looks like. Let's talk about what a washer is. So I pulled one out of the garage so you can see. This is a washer. It's relatively small. It's very, very thin, but it is actually a right circular cylinder with a hole punched in the middle of it. So it's more or less like one of these right here. These are also called annuli, or an annulus for singular. A-N-N-U-L-I for plural, A-N-N-U-L-U-S for singular. This is a right circular cylinder that has been rotated, and it has a hollow space on the inside. That's what we mean by a washer, something that looks basically like this. It is still a disc, but with a hollow space. So again, this is what's inside your faucet sink, trying to keep the sink from leaking. Let's go back to the screen and discuss how we can use this washer shape in order to compute the volume. We can see here that we're going to take these shapes and we're going to revolve them using washers. Let's take a look at the picture out of the textbook that explains where the washer shape comes from within the picture. You can see here that we have two curves. We've got the curve y equal to the square root of x, and we have the curve g of x equal to 1. That's the horizontal line y equal 1. When we're looking at them, we can see that the outer radius is produced by the upper curve, the square root of x, and the inner is produced by the y equal 1. They're being rotated around the x-axis. And I like to indicate that with a curved arrow to make sure I don't forget which one I'm revolving about. Now if you look at the next picture in the middle, the second one, you can see that we have this outer radius coming from the farthest away curve from the axis of rotation, and the inside, or the hole, which is being produced by the closest curve to the axis of rotation. It also gives us the surface that we can see in the picture on the far right. The hole that's in the center is being carved out by this closest curve, and the outside edge is from the outer curve, or the square root of x. In that way, we can see that we get an outer surface and an inner surface being carved out from the two graphs because the strips do not touch the axis of revolution. If the strips touched it, we would have the right value. You can see here the rule for the washer method about the x-axis. F of x and g of x are continuous and non-negative. We define R as the region bounded above by the graph of f of x and below by the graph of g of x. In the picture we were looking at previously, the axis of rotation is furthest away from the square root of x. This becomes the outer curve f of x. The inner curve is given by the curve that was y equal to 1. This is often called g of x. Here's the rule from the textbook about the washer method about the x-axis. Let f of x and g of x be both continuous and both non-negative. Define R as the region bounded above by the graph of f of x, below by the graph of g of x, on the left by the line x equal a, and on the right by the vertical line x equal b. Then the volume of the solid of revolution formed by revolving that region around the x-axis is given by the definite integral from x equal a to x equal b of pi times that radius squared. But we have an outer radius and an inner radius. This is what I mean by doing both at once. You're doing the outer radius and squaring it minus the inner radius and squaring it. Note that you could instead compute the volume of each one individually. You could do the volume of the outer one by doing the integral from a to b of pi times f of x quantity squared dx. and then subtract from that the volume of the inner radius revolved, which would be the integral from a to b of pi times g of x quantity squared dx. And then, of course, you subtract the inner volume from the outer volume to get the answer. This is doing it as two separate problems. Here, we are combining it into one integral. It can be done either way, and I don't know that one is a whole lot shorter than the other, though this is definitely somewhat shorter. Let's take the curve from example 4 and revolve it about the x-axis instead. We need to identify what the inner radius r sub I is and what the outer radius r sub O is. And yes, that's an O for outer radius and not a 0. Let's take a look at our picture again. We have the line y equal 3 up here at the top. We have the curve as well of e to the x for the bottom. I'm not sure why my picture is not wanting to draw. There we go. On the bottom, we have y equal, I believe, e to the x. Now, when we're looking at these, the close end of the strip closest to the axis of rotation forms the inner radius. This goes between the x-axis and the curve y equal e to the x. So the inner radius r sub I is e to the x. The outer radius goes from the axis of rotation to the farthest end of the strip, or the thin rectangle. In this case, it's going up to the line y equal 3. That means the outer radius is always 3, since the location of the upper end or furthest end of the strip never varies. Let's take a look then at what that means. That means that r sub I is given by e to the x, and r sub outer is given by 3. Now what we need to know is, what are the limits of integration? We're going to start on the left with x equals 0, and remember last time we got the right as the natural log of 3. That's the point of intersection between the curves y equal e to the x and y equal 3. Setting them equal and switching to logarithmic form gives you the form of the curve you need. The last strip touches the vertical line x equal the natural log of 3. By last strip, I mean if you were to draw a rectangle right there at the end, that's what it would be touching. The first rectangle would be all the way over here at the beginning and would be touching x equals 0 on the left. That means we go from x equals 0 to x equal the natural log of 3, pi times outer radius squared minus inner radius squared. Outer radius is 3. We square it to get 9. The inner radius is e to the x. We square that, and by exponent rules, we get e to the 2x. We can easily integrate the 9 to get 9x, and we can do a u substitution to get the integral of e to the 2x, which will give us 1/2 e to the 2x. Both need to be evaluated between 0 and the natural log of 3. The next thing we do is to evaluate and come up with our solution. Hopefully you can follow this, and if not, pause the video here and take a moment to study the work. Here's what that region looks like from Calc Plot 3D. We can see one sample rectangle which has been rotated, and you can just barely make out the shape here in the back. Y equal 3, the axis y equal to, or x equals 0, and the curve e to the x. Notice that we are rotating around the x-axis and it's producing a hollow space. This is what it looks like when you get it all done. If you were to look at it, this is more or less sort of like an arena shape where the floor would be the hole. Let's talk about the washer method rule for rotating around the y-axis. When we rotate around the y-axis, remember we have to solve for the x variable so that our functions are written in terms of y. Then we'll have f of y and g of y being continuous functions and not negative. Define R as the region bounded on the right by the graph of f of y, on the left by the graph of g of y, on the bottom by the line y equals c, some horizontal line, and on the top by the line y equals d, a different horizontal line. Then the volume of the solid of revolution formed by revolving y around the y-axis is given by this definite integral from y equals c to y equals d of pi times the different radii squared. The outer radius is squared first, and then the inner radius is squared second and subtracted from the outer radius squared. Let's take a look at example 6. In example 6, we're going to take the curve from example 3 and revolve it about the y-axis instead. We need to identify the inner radius, r sub I, and the outer radius, r sub O. Here's our shape again. Notice that there is a region where the inner radius is going to be 0 because the strips touch the axis of revolution. But there are also spaces where the strips do not touch the axis of revolution and the inner radii will not be 0. We have sort of, in a sense, two regions. One where the inner radius is the y-axis and the other where the inner radius is the curve x plus 1 quantity squared from x equals 0 to x equals 2. That means that we'll need to split it into the two regions. To split it into the two regions, we need to take the region where it is touching the axis of revolution and compute that volume either using the definite integral with pi r squared, or, since it's just a rectangle, we can compute it using the volume of the circular cylinder. When you rotate this rectangle about the y-axis, it will become a circular cylinder of radius 2 because the length here is 2. The height of it is 1, and that will become the differential dy. That's the distance between one circle to the next. That tells us that our volume for this little piece, when it's revolved, is pi r squared times the height between the two cylinders, or 2 squared times pi times 1, or 4 pi. Let's look at the second region. In the second region, starting here at height y equal 1 and going up here to height y equal 9, you'll notice that the inner radius does not touch the axis of revolution, which is the y-axis. Now what we need to do is compute again the inner radius and the outer radius. The inner radius goes between the y-axis and the parabola x plus 1 quantity squared. That means that the inner radius is given by that equation, x plus 1 quantity squared. The outer radius, on the other hand, is going out here to the edge where the value is always 2. That means that the outer radius is always the value 2. So we always have the same outer radius, which is 2. Now we need to solve the function for x so that we can get a function in terms of y. Our original function was y equals the quantity x plus 1 squared. We take the square root of both sides. Now, notice that we only include the positive radical because when we look at the parabola, we're only looking at the right arm of the parabola. The right arm of the parabola is the positive arm. The left arm is the negative arm. We include only the positive, and that gives us the square root of y. Then we move the 1 to the other side by subtracting 1. This gives us a function of the variable y solved for the variable x. This will match our picture now because the narrow end of our strip is the short end, which is vertical, which means the differential must be dy. Setting up our integral then, region 2 extends from y equals 1 to y equals 9, pi times the outer radius 2 being squared, minus the inner radius as a function of y also squared. Notice again that you can get the value for these here by looking at the graph and computing where they intersect. In this case, where does the curve x plus 1 quantity squared equal 2? It equals 2 whenever we're at 9. For x equal 2, rather. Sorry about that. And 2 then gives us the value 3 squared, which is 9. That's the y value at that point. Take a moment now, pause the video, and work out the solution to this definite integral. Then turn the video back on and compare your work to mine. I'm not going to explain every step of the integration, but basically you do have to multiply out this binomial type expression here by squaring it. Once you have that, you can integrate by doing the power rule for integration and then plug in the limits of integration. When complete, you should have 56 pi divided by 3. In this example, we rotated about the y-axis. What about rotating about lines other than the coordinate axes? We want to work one more example, and then we'll take a look at some mixed practice in the next video. This is one of the more difficult situations to set up when your axis of revolution or your axis of rotation is a line other than the x-axis or the y-axis. The reason is this affects the radius and how to compute it. Let's look at example 7. Find the volume of the region bounded by x equals 0 and the curve y to the 4th equal 1 minus x when rotated around the line x equal 3. Let's take a look first at what our curve looks like. We are bounded by x equals 0, which is another way of saying the y-axis, and the curve y to the 4th equal 1 minus x. Y to the 4th equal to 1 minus x is a region that looks like this. It's sort of close to a parabola been turned on the side, but notice it gets much flatter here towards the vertex. Now, because we have this expression here in this picture, we want to rotate it around the line x equal 3, which is over here. Imagine taking this shape and pulling it around this line. Notice that no part of the shaded purple region touches the axis of revolution. What does that tell you is going to happen when you rotate it? You got it. We're going to have a hole in the middle. Let's draw our strips perpendicular to the axis of rotation. When we do this, notice that the axis of rotation is vertical, so our strips are going to have to be, yes, horizontal. Let me put them on now. We've got strips that look like this. Notice that the short end of my strips is narrow and vertical, which must mean that the differential is going to have to be dy. That means that I will need to solve my equation for the variable x so that I can get it in terms of the variable y. But fortunately, ours already is. Now what we need to do is take this shape and put it over here. If I wanted to know what it looked like by graphing it briefly by hand, I would need to plot out the same basic shape being revolved. Here's what it would look like if it were 3 on the other side. I would have my shape coming out sort of like this and then coming back in. Then you can connect the top and the bottom with circles like this. This will give you an idea of what it's looking like on the inner part and the outer part. Once you complete these circles, you have to do circles for the outside. I find it much easier to use Calc Plot 3D or Geogebra 3D in order to know what it looks like. Notice that the end of the strip, in our case, is vertical, so it's dy. Always draw the strip perpendicular to the axis of rotation. Now we need to label the radius r, or if not all strips touch the axis of rotation, label the inner radius nearest end of the strip to the axis of rotation with r sub I, and the outer radius, the farthest end of the strip, to the axis of rotation with r sub O. Let's take a look at our picture now. you can see that I have labeled the inner radius from the axis of rotation, x equals 3, to the closest end of the strip here. That's r sub I. It would be r sub I on any of these strips. Going from the axis of rotation to the farthest end of each strip gives me the outer radius, r sub O. Notice I have this curving arrow to indicate the axis of rotation is x equals 3. Now we need to compute expressions for the radius and the height. How are we going to accomplish that? By height, I mean the distance here that we see, the height of each strip, not the height of the circular cylinder, which will always be the differential, in this case dy. When I'm looking at the height of each strip, I need to realize that in general, from the axis of rotation to the far end is 3, but from the axis of rotation to the close end is the x value on the curve, y to the 4th times, or y equal, I can't even remember what it is now, 1 minus x to the 4th, I think. So when we're looking at it, the x value on the curve subtracted from the distance of 3 gives us the height of each individual rectangle. Why is that important? The height of the rectangles is basically going to give us the radius of the circular cylinders. The height of each rectangle is that radius. Now let's take a look at what else we have. We've still got our outer radius and our inner radius for revolving, and we've got the height of each rectangle, which gives us the basic radius. Let's see what we need to do next. We saw from our previous picture that the height of each strip was given by 3 minus the x value on the curve. Now what we need to do is convert that into something related to our curve, which is y to the 4th equal 1 minus x. To get the x value, we solve for x, which gives us 1 minus y to the 4th. So our height then is 3 minus x, or 3 minus 1 minus y to the 4th, which gives us 3 minus 1, or 2, and a double negative gives us plus y to the 4th. What is our inner radius? Let's take a look back at the previous picture. In the previous picture, our inner radius is basically coming to the curve itself, and the outer radius is going to the outside, which is 3 wide. Looking back now at the work we have, our inner radius is 3 minus x on this curve, so the inner radius is the 3 minus 1 minus y to the 4th, the quantity, which is 2 plus y to the 4th. The outer radius is the x value on the y-axis, or 3 minus 0, which is just 3. Now when we finish the rest of the problem, we need to find the limits of integration if we're integrating. Since we are integrating with a differential of dy, we want to find the bottommost strip to the topmost strip. Looking back at our picture then, we have a bottommost strip here at -1 and a topmost strip up here at 1. That means that our limits of integration run from y equal -1 to y equal 1. Let's set up our integral. In this case, we have y equal -1 to y equal 1 of pi r squared dy, since we are rotating around the y-axis. That makes our limits of integration -1 to 1 and the differential dy. Remember, we have to do r outer squared minus r inner squared. Our r outer was given by 3, and our r inner, after simplification, was 2 plus y to the 4th. Go ahead and pause the video here and complete the integration, and then turn the video back on to compare your work to mine. This is a very straightforward integral that only requires you to multiply out the binomial square and to square the 3 to get 9. Integrating using the power rule and then plugging in the limits of integration should bring you to the result of 368 pi divided by 45. This is what the basic shape looks like when you rotate it in Calc Plot 3D. Here's our shape here with some sample rectangles drawn. Notice the differential is dy. Now we rotate, and in fact not around the y-axis as I said earlier, but around the line x equals 3, which I forgot. Since we're rotating around here, notice that the inner edge is carving out the hole, and the farthest end is carving out the outer region of the surface. When we get it done, we have the outer region being given by the far end, which is basically a cylinder of radius 3, but the inside is carved out by this shape right here, y to the 4th equal 1 minus x. When we look at it, it looks something like this, which is kind of a fascinating shape. This is the end of this video on using the disk and washer method to compute volumes of revolution. In the next video, we'll do some mixed practice samples.